next we will be looking into how to construct the SLR parsing table. First we have already seen the technique. So, we will formally put it in the form of an algorithm. So, first we construct the LR0 set of items, sets of items. So, this is the first step. So, it first convert the grammar G into an augmented grammar G dash by adding the extra start symbol, like if the grammar start symbol is say E, then we add another extra production E dash producing E, with the idea that when when the parser will try to do a reduction by this particular rule. So, it will mean that the string has been parsed successfully. So, that way we start with the item like E dash producing dot E, and that is, and we take the closure of this. So, that will make the set I 0, and from this set I 0. So, we will be see on various input symbols and grammar non terminals also. So, we will be having other items produced. So, I 0 I 1, suppose when we construct the items. So, we get these items like I 0 I 1 up to I n. So, that is that is the collection of LR 0 items for the grammar. Now, from this, so from the state I, we will be constructing the set I. So, for each of these for each of these I 0 I 1 etcetera. So, they will constitute one state. So, this will constitute the state S 0, this will constitute the state S 1. So, like that, and we will from this state. So, once we call these the states. So, we will be looking into the go to parts. So, we have previously seen how to construct the go to of symbol of a particular state on some terminal or non terminal symbol, and we have also seen like how to get the closure. So, if this A producing alpha dot A beta is an item in a particular set of items, then that is in I. So, if I have got a item like A producing alpha dot A beta, and the go to A says it is a new item I j, then in the action part of the table we will add the corresponding to state number I and input A, we will add the action shift j. That means, it will do a shift operation and it will come to a new state which is j. So, that is the meaning of this rule. So, we can look into a particular example like say this one. So, while constructing this table from the state I 0. So, I 0 is having E dash producing dot E and the closure of that. So, if from there we will get say dot E will have the ID also. So, on ID it will do a shift and it will come to state 5. So, if we just go back a few slides, say on I 0 on ID it comes to the state I 5 comes to the item I 5. So, accordingly I will be adding this entry in the table shift and the new state is 5. So, that is the way this table is constructed for the shifting part. Now, if you have got a rule like this A producing alpha dot, if you have an item in the set I like A producing alpha dot, then we will first have to see what is the follow of this non terminal A, and for each of the symbols small a in the follow set of A. So, we will be adding this production reduced by A producing alpha. To understand this thing, so let us look into so how do we, for example, how do we get this particular rule, how do we get this particular reduction. So, this I 3 and on plus it is R 4. So, I 3, so it means the reduced by rule number 4. So, rule number 4 is this one T producing F. So, I have to see what is the follow set of T. So, follow set of T, follow of T is given by, so T is followed by this star, because by this rule. So, this is followed by star, and by this rule E producing T, whatever is in follow of E is in follow of T. So, I will get plus, and here E is followed by closing parenthesis, and also since E was the start symbol. So, dollar was there in the follow set of E. So, as a result the follow of T will have the star plus close parenthesis and dollar. So, you see for this plus star close parenthesis and dollar we have added the action reduced by rule number 4. So, this is done here. So, this way we can we have to for all the symbols that are coming in the follow set of the terminal non terminal on the left hand side of the production. So, we have to have this we have to add the corresponding rule there. Next, for particularly for this S dash producing S dot, where S is the actual start symbol of grammar G and S dash is the start symbol of the augmented grammar G dash. So, if S dash producing S dot giving S dot, if this item is there, that means I am trying to do a reduction by this particular we are trying to do a reduction by this rule S dash producing S. So, if in a particular item you have this thing, then action I dollar is set to accept, means action I dollar means I am currently in state I and the next input symbol is dollar. So, input is the input string is also exhausted and I am trying to do this reduction. So, that is naturally the accept state. So, the main difficulty here is one thing is that you have to calculate these items carefully, this item calculation. So, that is one job, and the other job is to compute the follow of all the symbols of all the non terminal symbols that you have in the grammar. Wherever you will be requiring this A producing alpha, this type of rule. So, you need to have the follow set of A. Now, if there is any conflict, like while doing this putting these actions shift and reduce. So, if there is a conflict, then the grammar is not an SLR grammar. So, like say in the previous example that we took. So, if you look into the action part, you see there is no entry where there are two actions are defined. So, everywhere it is either a shift operation or a reduce operation or there is no operation. So, no operation means it is an error, but or the action is accept. So, those things are there, but there is no entry in this table where the actions are multiply defined. So, this table this particular grammar is an SLR grammar, because we could construct the SLR table for them without any problem. And then for the go to part, so if you look into this table, so there are two parts, one part is the action part and the other part is the go to part. For the go to part, I have got the non terminals E, T and F, and from individual items individual sets of items. So, on the non terminal the go tos have been calculated. So, here the corresponding go tos are added. For example, from state say from item I 0 on E, T and F, let us see where we are going. So, if we look into this particular diagram for I 0, on E it was going to state I 1, on T it was coming to this one 12, and here it is not marked, the label is not marked, but it has come from this T producing F dot. So, this is F. So, this I 1, I 2 and I 3. So, these are the three states to which we can go from the state I naught. So, that is done here. So, you see from the state 0 on getting this E, T or F. So, it is moving to the states 1, 2 and 3. So, in this way the go to part will be filled up. So, once this action part and go to part has been made, then we can use the algorithm that we have seen previously, this parsing algorithm for parsing the input string. And at the end, so if you are finding that okay, we are at a state where the action is accept, then parsing is over. If there is an error in the input stream, then at some point of time you will be landing into one of these entries which is blank in this table, and if the entry is blank, that means the input there is some error. Okay. And of course, if you come to this dollar and this thing, so the accept state, then it is accepted. And if there are if some entries are multiply defined, then there is problem, as I said that the grammar is not SLR, because the parser will be confused whether to do a shift operation or a reduce operation. or it may so happen that both the actions are reduce of actions, but they are by two different rules. So, the parser will not know clearly like which rule it should use. So, that way it can give rise to the shift reduce conflict and reduce conflict. So, those conflicts are to be ideally they should not be there in the parsing table. So, if for a grammar we have a situation where these conflicts are not there, then we will tell that the grammar is an SLR grammar. So, let us look into an example which is not SLR. Okay. So, let us look into this grammar where we have got this thing, this S producing L equal to R or R, L producing star R I D, R producing L. So, here this star I D and equal to, so these are terminal symbols, S, L and R, they are non-terminal symbols. So, initially I will have the state, so with this I will be adding this additional rule S dash producing S to get the augmented grammar G dash. Now, on this augmented grammar we try to construct the sets of items. So, this I 0 is S dash producing dot S, then the closure of that. So, S producing dot L equal to R, S producing dot R, they will be coming from this rule, then L producing dot star R or L producing dot I D, and again since dot R is there. So, R producing dot L will come. So, that is I 0. I 0 to I 1. So, S dash, so it is go to I 0 S. So, go to I 0 S is I 1. So, which is this one. Similarly, from go to I 0 L. So, this I 0 to I 1. So, this is go to I 0 S, and similarly from I 0 to I 2 it is go to I 0 on L. So, that way similar other items are constructed accordingly. So, I am not going to that explanation, but let us look into this item more carefully. Say this item I 2. So, S producing L dot equal to R, that means at so the first item says that I have seen a portion of the string where from which I can derive L, and I am expecting the next input symbol to be equal to. Now, what is the action? Now, since the since it is equal to, so if the next input symbol is equal to, I do a shift. So, the first part will tell us, first item will tell me that. Second item telling me no, if you even if you see equal to, so you better do a reduction by this rule. So, you better do a reduction by this rule, R producing L dot. So, you have to look into the follow set of R. So, you have to look into the follow set of R, and for all the terminals in the follow set of R, you have to reduce by R producing L. So, what is the follow set of R? So, follow set of R is equal to, so here by this rule L producing star R. So, whatever is in follow of L is in follow of R. So, follow of L is equal to follow of R, follow of R will contain follow of L, it may contain something more, but it will have this follow of L, and follow of L has got this equality symbol. So, you see among the other symbols, this equality symbol will definitely be there. So, follow of L contains equality. So, when I am doing the action, the first one, the first rule says that, so by this rule S producing L dot R, L dot equal to R. So, from I 2 on equality it goes to I 6. So, from I 2 to I 6 this is go to I 2 equality. Okay. So, this is a shift action. So, naturally it tells me if I get an equality, I should do a shift and the new state will be 6. So, that is coming from this particular rule. Now, this rule telling me that you should do a reduction for which symbols? For all the symbols which are coming in the follow set of R, and the follow set of R contains equality. So, that means if you see an equality, then you should do a reduction by R producing L. So, this is giving rise to a shift reduce conflict on the symbol equality. So, whenever if you are trying to draw the parsing table, then for the state 2 and for the input symbol equality, I will have two entries. One is shift 6, another is reduce by rule number 1, 2, 3, 4, 5, 6, reduce by rule number 6. Okay. That way I will have two actions. So, this is this particular grammar that is given is not an SLR grammar, because it has got multiply defined entries for some of the multiply defined values for some of the entries. So, that has to be taken care of. So, what is the solution? So, one solution is that you modify the grammar. So, you modify the grammar, whether it will catch the language syntax properly or not, that is a question. If you can modify the grammar and make it SLR, it is well and good. So, if we cannot, then we have to go for more powerful parsing strategy, like say we have to go for something called say LR parser, called canonical LR parser, which is more powerful than SLR parser, but it will have more complexity. The complexity of this SLR parser, we will see that it is going to be much more compared to this SLR parser. So, they are known as canonical LR, sometimes it is called CLR or sometimes it is called just LR, and this SLR parser is often called LR0 parser. Okay. So, in case of LR, this canonical LR parser, we use some look ahead symbols for items. So, they are called LR1 items. So, they are not LR0 items. So, they are called LR1 items. So, from the current position, you do not only look at the current input symbol. So, what it means is this thing, that if this is your input stream, then at present suppose you are at this position. So, your input pointer is here. So, in case of SLR parser, we were taking a decision based on this particular input symbol only, but in case of LR1 parser, we will be looking ahead by one more symbol. So, we will be looking into the next symbol also and accordingly take a decision. So, if we do that, then many of these conflicts that we are getting, so shift reduce or reduce reduce conflicts, so they may get resolved, so as we are doing a look ahead. So, but the difficulty is that it will result in a large collection of items. So, so that way the complexity of the parser will be very high. And there is another variant which is known as LALR parser, where look aheads are introduced in the LR0 item. So, here also it is there, but here the number of states will be much less compared to this canonical LR parser. So, so SLR parser, for most of many grammars, so you can do the parser construction by hand. Canonical LR parser, so it becomes difficult, because with as you are increasing the complexity of the grammar, so number of states will become pretty high. And LALR also, since it is depending on these LR1 items, so it will be again be difficult to construct by hand, but they can be automated very easily. So, we will see that the automated tools for this parser generator, so they will generate LALR parsers, because of the reason that LALR parser ultimately the number of states will be same as LR0 or SLR parser, but power wise it will be as powerful as the canonical LR or LR1 parser. So, we will see how they are done. So, let us look into the LR1 grammar. A grammar will be said to be LR1 if in a single left to right scan we can construct a reverse rightmost derivation while using at most a single token look ahead to resolve ambiguities. So, in case of LR0, so we were not doing any look ahead. In case of LR1, we are doing look ahead by at most one token. So, you may or may not require to take may or may not need to base your decision on the next input symbol. Maybe at current input symbol only you can take a decision, but in case of confusion, okay, so you can you are allowed to look into the next token and then take a decision. So, and it will just like any other this LR parser. So, it will be doing a reverse rightmost derivation. So, it is a bottom up parser and it will be doing a rightmost derivation. So, at every step the rightmost non-terminal symbol will be replaced by the corresponding right hand side of the production rule. In general, LRK parsers they will be using K token look ahead. So, they will be more and more powerful. So, as you are trying to allowing more and more look ahead, then the parser becomes more and more powerful. However, the parser complexity will also increase significantly. So, normally we go with this LR1 parser, we do not go beyond that, because most of the programming languages and the constructs that we have. So, LR1 is good enough. So, we do not need to go beyond that. Okay. So, what is an LRK item? So, for all our discussion, so we will be taking k equal to 1. So, you can just generalize it to other values of k. So, this LRK item, so it is a pair alpha semicolon beta, where alpha is a production from G of the grammar G with a dot at some position in the right hand side. So, this alpha part is similar to what we have in the LR0 item. So, this alpha part is same as that one. For example, if you have got say A producing x dot y z. So, this was an item in case of LR0 parser, but in case of LR1 parser there will be another look ahead string that contains k symbols at most there. So, look ahead string that will contain k symbols. So, if I am using k equal to 1, that means I will have a single say terminal symbols after this. So, this is an item A producing x dot y z semicolon A. So, what is the meaning of that we will see. So, basically this part will be giving me the look ahead. So, what we are going to do a look ahead. Now, as I am doing this, since the items they have got two parts, one part is a rule with a dot somewhere and the other part is a terminal symbol or a terminal string, then there may be several such items where the rule part is same, okay, rule with dot. So, that part is same, what differs is the beta part. So, they are said to have same core. So, this is called the core, and maybe so these two items, if you see, both of them are having A producing x dot y z as the core. So, they have got the same core, but the next item, that next look ahead token is different. Here it is A, here it is B. Now, if I have got say a situation where this thing occurs, then many a time we will be writing in a shorthand form like this: A producing x dot y z semicolon, then within brace. So, we write all the alternative strings for which this is an item. So, in this particular case, so we have got two such items: A producing x dot y z semicolon A producing x dot y z semicolon B. So, we combine them together while writing as A producing x dot y z semicolon A comma B. So, this way we will be representing LRK items, where we remember that this part is meaning of the core part is same as what we have done, what we have in case of LR0 item. So, this means that we have for example, say this one A producing x dot y z, this means we have already seen a string which is derivable from x, and after that this dot is there, that means we are expecting to see a string which is derivable from this y z. Okay. So, that was the meaning. So, this is fine. So, this look ahead part, look ahead token, so this will be clear after some time. So, we will be explaining why this is what is this and how is it going to help us. So, as such, for most of the time, so this is like a baggage that we carry with the items. So, this look ahead items, so we carry them along to allow choosing correct reduction when there is any choice. So, this is particularly, this look ahead will be particularly useful when we are going to have this reduction rule. So, in that case, when there is a confusion in the reduction process, so then we will be taking help of that. So, we will be either using that reduction based on the two or more these tokens, this look ahead token. So, based on that we will take a decision, whether to reduce by one rule or the other, or whether to do a reduction or not. Then so look aheads are basically bookkeeping. So that way, so they are bookkeeping. So unless we have got an item that has got a dot at the right end. So like if you consider say these two rules, these two items. So for this item there is no direct use. So from this item, so we can try to generate say go to the item and y. So we will be simply getting an item x y dot z, and this part will be carried forward, this a part, this token part. So this will be carried forward. So it is a look ahead. So it is just a bookkeeping. Whereas for this particular case where this dot is at the end, then it is going to be useful. How is it going to be useful? Suppose I have I am at a state say I 5, where I have got these two items. So A producing x y z dot semicolon A and B producing x y z dot semicolon B. So previously what we were doing? So if we have to do a reduction, then this rule tells me that for all the terminal symbols for the in the follow set of A, I have to do reduction by this rule, and this rule is telling me that for all the terminals in the follow set of B, I have to do by this reduction. Now, if the grammar is such that this follow set of A and follow set of B, they have got some terminals common between them, then this will immediately give rise to a reduce conflict. Now, what this A and B is going to do is that it is trying to modify the context. So, it will see whether the next input symbol is A or not, and this will see if the next input symbol is B or not. That is the look ahead token. So, the look ahead token is A, then only this reduction will be done. If the look ahead token is B, then this reduction will be done, and since these two tokens are different, they are not same token, then we can definitely take a decision. So, that reduce conflict will get resolved in this fashion. So, we can decide between reducing to A or B by looking at limited right context. So, we are not doing a very large amount of look ahead, we are looking ahead by a single symbol, single token, and then we are taking a decision. So, that way it is going to be powerful. So, if the follow set of A and B are totally disjoint from each other, then of course, it would have been an LR0 grammar. So, it would have been an SLR grammar, but if they are not disjoint, the A and B follow set of A and B, if they are not disjoint, then this grammar will not be an SLR grammar, but with this if this look ahead tokens are different, then this grammar is definitely an LR1 grammar. So, this way it will be helpful in this look ahead token, they can be utilized for resolving the reduce conflicts between a number of rules. So, but the problem is that you see that similar items, so they will go on coming, only the look ahead part may be different. As a result, they will give rise to large number of states or large number of items, and that is the thing. So, number of states that you get with this LR1 parsing policy, it will be much larger compared to the LR0 parsing policy, and this is exactly the reason why this thing happens, because if we had relied only on this rule part, this dot, this left side, so the A producing x dot y z, then number of states in SLR and this canonical LR, they would have been same, but because of this look ahead token, so they are going to be different, and they are going to have more number of states in case of this canonical LR parser.